In Unit 4, Lesson 5, we are looking at a practice understanding task called Be There or Be Square. So in this task, we have Optima's niece, Jenny, who works at a shop taking orders and drawing quilt diagrams. When the shop isn't too busy, Jenny pulls out her math homework and works on it. One day, she is working on graphing parabolas and notices that the equations that she is working on looks a lot like an order for the quilt block. For instance, Jenny is supposed to graph the equation y equals x minus 3 squared plus 4. She thinks that's funny. This would be an order where the length of the standard square is reduced by 3, and then we add a little piece of fabric that has an area of 4. We don't usually get orders like that, but it still makes sense. I better get back to thinking about parabolas. So the first thing we want to do here is describe what that parabola is that Jenny's been assigned to graph. So the first thing you should have noticed here was that if it was reduced by 3, that would have shown a shift to the right 3 units. And that is to the right 3 units because the shift of the x-axis is occurring prior to any shifting vertically along the y-axis. And then the problem said that it was plus 4. So this would have also would have represented a shift up 4 units. All right, so that's kind of what the graph would look like if Jenny were to graph it. So it says that she returns to her homework, which is about graphing quadratic functions. Much to her dismay, she finds that she's been given x squared minus 6x plus 9. Oh dear, she thinks. I can't tell where the vertex is or identify any of the transformations of the parabola in this form. Now what am I supposed to do? She says, wait a minute. Is this the area of a perfect square? So we're going to use our work from building the perfect square to answer Jenny's question and justify our answer. So let's think about building a perfect square. So if we have a square here that Jenny starts with, which has side lengths of x, and it says that there are negative 6x. So if I think about negative 6x, that's going to be a subtraction of 3 from each side. All right, so that would give us minus 3x here, minus 3x, and then a positive 9 at the top. And that does happen to satisfy the entire problem. So this is a perfect square. That problem can be shown by completing the square. So question 3 says that Jenny says, I think I figured out how to change the form of my quadratic equation so that I can graph the parabola. I'll check to see if I can make an equation a perfect square. Jenny's equation is again x squared minus 6x plus 9. So we want to try to change the form of the equation, find the vertex, and graph the parabola. So a moment ago we had the diagram drawn where we had negative 3x's and a positive 9. So this was negative 3 on either side where we took 3 away from the entire length of the x. So that means our equation can be x minus 3 squared, can represent our new function. So the vertex of the parabola in this case would be that negative 3 becomes a positive and 0. We didn't move up any or down any. We only moved to the right 3 units. So now we want to graph this with at least 3 accurate points. Okay, so when I think about graphing this, I'm going to first start with my vertex 3, 0. And then I'm going to go over 1, up 1, because this is just a standard a value of 1, over 2, up 4, and if I can, over 3, up 9, Puts me a little off the graph, but that's okay. I'm going to then mirror those on the other side of my axis of symmetry so that I can create my graph. And this would be, excuse the fact that I'm a little off, but that would be the graph of our function. Okay, so then it says the next quadratic to graph on Jenny's homework is y equals x squared plus 4x plus 2. Does this expression fit the pattern for a perfect square, y or y not? And so let's think about that problem. X squared plus 4x plus 2. So if I draw my x squared, 4x means I need 2 little boxes on each side. And that will put plus 2 means that at the top of this, I actually only have 2 little boxes. And that is not a perfect square. So we're missing 2 boxes, if the small boxes, if we're going to be a perfect square. So we're going to use the area model to figure out how we can complete the square so that the equation can be written in vertex form. So if we think about this, a square would have in this, if the problem was a perfect square, our equation would be x plus 2 squared. But what ends up happening is that's creating a box or a square that has a total of 4 boxes up in that corner. And we only need in this corner 2 boxes. So what we're going to have to do here is we're going to have to remove those 2 boxes that we don't need so that we have the same problem. So we have x plus 2 squared, and then we're going to take away the 2 extra boxes that would be created if we made that square. Now it says, is the equation you have written equivalent to the original equation? So we can test this by using our area model that we break into quarters and solve this. So we're going to say x plus 2 times x plus 2. This would give us x squared, 2x, 2x, and 4. So our equation becomes x squared plus 4x plus 4, and we're going to drop down that minus 2. So now what we end up with is when we subtract these 2's, we have x squared plus 4x, and subtract that 2 from 4, and we have plus 2. And now this is the same equation that we began with. So identify the vertex and graph the parabola. So if I'm going to identify my vertex here, my vertex would be -2, -2. And then I would graph it by going over 1 up 1, over 2 up 4, and over 3 up 9. Each of those movements is from the vertex. And then I would mirror each of those points and connect them with a line. Alright, so there's our graph of this function. Now that Jenny has figured this out, she's hoping that she's not going to have to complete the square for an equation where b is an odd number. But of course, that's the next problem. So let's think about what Jenny's going to have to do here. So again, Jenny starts by saying, okay, I'm going to draw my square. And in the last couple of problems, what Jenny's done is she's divided that b term in half. Well, in this case, that b term divided in half becomes a decimal. And that's okay. What we can do here is put 3.5 on either side. And we will have 3.5x on either side of our function to represent the 7. Now, to get the upper corner of this, we would need to multiply 3.5 by 3.5, which will give us 12.25. So what we have to look at now is the vertex form of this problem would be g of x equals x squared, or excuse me, parentheses, x plus 3.5 squared. And then we need to take into account that we only are supposed to have 10 in our box, or for this function, but our square that we have built has 12.25 units. So in order to get 10, we need to take away 2.25 units. And that would be the answer for the vertex form of this particular problem. So her vertex would be a negative 3.5 and a negative 2.25 for her vertex x and y value. Now, if you kind of struggled to see that one, let's do another. So here we have x squared minus 5x, so that means we need a negative 2.5x on both sides, which will give us 6.25 in the upper corner. So our vertex form here would be x minus 2.5 squared. Now here we have 6.25 units, but we need 3. So we need to take away 3.25 of those units. So our vertex in this situation would be a positive 2.5 and a negative 3.25. Okay, and the last one of this situation is another one with, this time, just a negative 1. So this means we're going to have to put a negative 0.5x on each side. And when we multiply that, we're going to get 0.25 in our upper corner. So our vertex form here would be g of x equals x minus 0.5 squared. Now we have 0.25 and we need negative 0.5, so we're going to have to subtract negative 5.25 in this case. I'm sorry, that 5's a little rough. So our vertex here would be a positive 0.5, negative 5.25. Okay. So to finish everything up, Jenny gets a parabola that has an a value of 2. So now she's got to think about what this is going to mean. So she's going to draw 2 squares because she has 2 x squareds. And she's got 12 little inches added to, or subtracted in this case, from each side. So we're going to think about the fact that she's got to divide that evenly among both things. So that means each square needs a total of 6. So we're going to have negative 3 x's in each of these little side pieces that have been taken away. So therefore, in each corner, there will be a total of 9. So when we're looking at this and writing vertex form for this problem, her function will be h of x equals 2 times x minus 3 squared. Now for her 17, she's got a total of 9 plus 9, which is 18. She needs 17, so she's going to take away 1. Therefore, her vertex is going to be a positive 3 and a negative 1. And then she's going to go over 1 up 2, over 2 up 8 because she's doing this twice. So 1, 2, 3, 4, 5, 6, 7, 8. And we're just going to mirror those 2 points in this case and connect them for her function. All right, so she closes with another one that has a half this time. Okay, so in this case, let's think about what happens to just a standard square. So if I have half of a square, so this is my standard, and when I have half, I have 2 x's. So let's again go back and think about that. If I have 2 x's when I have half, when I have a whole, I have 4 x's. All right, so that's a 2 on each side. That would give me a total of 4 in my corner. But in this problem, what we're going to do is we're going to have half of this function. So half of x plus 2 squared. That's what this problem is saying, is I want half of that. Half of x plus 2 squared. So if I'm finding half of this, then when I do the corner, I want half of what's up there. There's 4 up there, so I only want 2 of them. In order to get negative 3, if I'm at 2, I need to subtract 5 to get to my negative 3. Therefore, my vertex here is at negative 2, negative 5. And this particular problem has a shrinking value. It is a vertical compression by a factor of 1/2 in this particular problem. And that concludes your lesson 5.